All right, today what we're gonna do is we're gonna talk a little bit about symmetry, and symmetry with respect to three places. Okay, we have symmetry with respect to the x-axis, the y-axis, and the origin. Okay, you're gonna be able to, when I'm done, you're gonna be able to tell if a graph has symmetry to the y-axis, to the x-axis, or to the origin, based on either a picture, a set of ordered pairs, or an equation. Okay, that's what you're going to be able to do. Do you know what symmetry is? Okay, symmetry is something that if you fold something at a certain spot, then if you folded it, the one side would match the other side. For example, we took a test on the quadratic function, and what we did was we graphed it, and we saw a picture like this. And why does a quadratic function have symmetry? Because if you fold it along the axis of symmetry, which that's what it's called, axis of symmetry, the left and the right side would land right on top of each other. So, but we're not going to talk about symmetry to any line. We're talking about symmetry to this line, the y-axis. So if this parabola were right here, and the axis of symmetry were the y-axis, then you would say that this has symmetry to the y-axis. So when we talk about the y-axis, I am talking about this axis right here. And if I talk about symmetry to the x-axis, I am talking about this. So something that looks like this, a parabola on its side, that has symmetry to the y-axis, or to the x-axis, I'm sorry. Okay, so let's take a look at this picture right here. And we're talking first about symmetry to the y-axis. If you were to fold this graph, and by the way, this is not a function. This oval right here is not a function. But if you were to fold this along the y-axis, would this left side and the right side land on top of each other? Okay, now you're going to be able to do this two ways. Looking at the picture, and you're going to be able to do it by looking at the ordered pairs, and you're going to be able to do it by an equation. First of all, look at your picture. Does it appear that if you were to fold this or cut along the y-axis, would they line up on top of each other? Does it appear that? Yes. Now look at their ordered pairs. See this point? This is 6, 3. And this is negative 6, 3. If I told you this point right here is, let's say 1, 7. This point is going to be negative 1, 7. This point, let's say this is, let's say it's 2, 6. This point is going to be negative 2, 6. What do you notice? What do you notice? What's happening to my ordered pairs? The x value is the opposite. So in other words, what I'm doing is I'm taking half of my graph and I'm reflecting it over the y-axis. And how do you reflect something over the y-axis? You simply change the x values to be the opposite. Okay? So, if you see a picture and you look at some of your ordered pairs, a graph will have symmetry to the y-axis if for every x value, every ordered pair, if the x value changes its sign, then it has symmetry to the y-axis. Now, how do you prove it mathematically or algebraically? What you do is you will replace, for y-axis symmetry, you're gonna take all your x values and you're gonna change their signs. You're gonna put in, for x, you're gonna put negative x. And you're gonna algebraically do the problem. If you can get the problem, the equation back to its original state, then it has symmetry to the y-axis. So let's look at an example right here. Okay, so, and this just tells you, for a graph to have symmetry to the y-axis, their y-coordinates will be the same, their x-coordinates will be opposite of each other. Okay, so that's what I really want you to pay attention to. So, this is the directions. What you do, a graph is symmetric with respect to the y-axis if whenever xy is on the graph, then negative xy is also on it. And also, in algebraic terms, what you do, you replace x for negative x, and if you produce an equivalent equation, then it has symmetry to the y-axis. So let's take a look at an example. Look at this. We've got y equals x to the 4th minus 5x squared plus 3. Is this symmetrical to the y-axis? What you do is everywhere you see an x, you're going to put in a negative x. And let's do this problem. So, right here, you leave y the same, and where you see an x, you're going to put in a negative x. And evaluate this, do the math. What is a negative number to an even power? What does this come out to be? We had to simplify this. It's positive. So this is going to be x to the 4th. What's a negative to an even power again? It's going to be a positive. And did we get this, we evaluated it or simplified it. And did we go back to its original? Every term has to be exactly the same. Yes. It has symmetry to the y-axis. Okay. Now, what if I asked you to graph this? What would you do? I would type in my calculator, I would type in x to the 4th minus 5x squared, and then plus 3. You could just look on my calculator here. Okay, that is the picture. If I were to fold this on the y-axis, does it appear that the left and the right side match? It does. So the picture, what you do is fold it along the y-axis. And now let's look at our table. Second table. What you'll see if, what you're going to want to do is change, if 1, negative 1 is on the graph, then negative 1 is on the graph. So what you're doing is you're changing the x values. For every x value here, you've got the opposite. So we have 1, negative 1, so negative 1 is on the graph. Check this one out. 2, negative 1, so negative 2, negative 1. So you can look at your table of values also. Okay, so for every ordered pair that's on the graph, if it's going to have symmetry, so I could find, on my table, I could find negative 3, 39. Let's see. There it is. And any point, all you do is change your x values. Now, if a graph has symmetry to the y-axis, it has another name. It's called an even function. You have to know this. So on your test, it has another name. If a graph has symmetry to the y-axis, we call it an even function. Okay. Now go to the next symmetry. X-axis symmetry. Here's a picture of a graph. that has symmetry with respect to the x-axis. And if I looked at the picture, all I would do is I would fold this along the x-axis, and if the top part matched the bottom part, I'd probably say yes. Now how can we test it with points? Check out this point. This ordered pair is 2 square root of 5. And if 2 negative square root of 5 is on the graph, then that's a possibility. Do a few more. If this ordered pair is 0, 3, then guess what this one is? 0, negative 3. If this is negative 2, 1, this is going to be negative 2, negative 1. What am I doing now for x-axis symmetry? What am I doing? Taking the y values and switching their signs. I'm leaving all the x values to be the same. So if a graph has symmetry to the x-axis, you can look at the picture and fold it or cut it along the x-axis, and if they match, then that's an indication. If the x values are the same and the y values are the opposite, then there's another test. And how do you think you do it algebraically? What do? You're going to replace, to test for x-axis symmetry, you're going to replace y for negative y, and then you're going to tell me if it has symmetry or not. So let's do one. Let's do this example, example 2. So algebraically, what you do is you will replace, for x-axis symmetry, you're going to take all of your y values and you're going to put in negative y. So right here is a y value. You're going to write negative y squared equals 4x minus 12. Now simplify it. If you have an even power, what happens to it? And you get this. Did we get this equation back to its original state? Yes. So this has symmetry to the x-axis. Let me show you one that doesn't. Here would be an example. If we replaced y for negative y here, this is what you get. And you simplify this, this is going to still stay negative y to the third. And what you're going to try to do is multiply everything by negative 1 to get y cubed back to a positive. But what's going to happen is this is going to change to negative 4x, and this is going to be a positive 12. So no, we didn't get it back to its original state. So this one does not, this equation does not have symmetry to the x-axis. Okay. There's one more type of symmetry. Origin symmetry. Where is the origin? 0, 0. Here's a picture of something that has symmetry to the origin. What you do, you pick any point on one side in one part of the graph. If you can draw a line through the origin, and notice that both of the ordered pairs, so if this point is, let's say, I'm going to make this up. If I said this is 3, 4, then guess what this point is? It's negative 3, negative 4. If this is 1, 2, then if I were to draw a line through here, guess what this point's going to be? Negative 1, negative 2. And these two segments here and here will be equal. So, how do we know if the picture is going to be symmetrical to the origin? Well, you do exactly what I did, and I would look at these right here. See if these are equal, and also if both ordered pair, if you switch both of the signs, then it has symmetry to the origin. How would you prove it algebraically? Well, if 3, 4 is on the graph and negative 3, negative 4 has to be, then what you do is you take all of your x values and you're going to put in a negative x, And you have to do both of these. Every y value, you're gonna put a negative y. And then if you can get the equation back to its original state, then it has symmetry to the origin. So let's try this example. What are you gonna do? You're gonna replace both variables. So you're gonna take this one and you're gonna put negative y equals negative x cubed over 10 equals, minus x. And it's going to be a minus a negative x. So now let's clean this up. You end up with negative y equals negative x cubed over 10, and then this is going to be a plus x. Did I get this back to its original state? No. But could I? How could I? If I multiply everything by -1, am I allowed to multiply everything by -1? Yeah. And this is going to be a positive y now. This is going to be a positive x cubed over 10, and this is going to be a negative x. All I did was I multiplied this whole thing by -1, and it's back. It's back to its original state. Now let's graph it and check out the ordered pairs. So I'm going to type in parentheses, x to the third over 10, and then minus x. And I'm going to graph this. Okay, there's the picture of it. So if I were to pick a point and go through the origin, does it appear that all of these segments are going to be equal? Yes. Now let's look at our table. If I hit second table, for every ordered pair that you see, so let's name this point. This is -3, 3. If -3, 3 is, actually that's a 0.3, right? That's a 0.3. -3.3. If -3.3 is on the graph, then -0.3 is on the graph. And there it is, right there. If -1.9 is on the graph, then -0.9. So that's how you can look at the table of values and tell me if it has symmetry to the origin. Now, for origin, it has another name. It is called an odd function. So if I say, is this an odd function? It's the same as me asking you, does this have symmetry to the origin? I remember it O and O, odd and origin. Now, the one that did not have a special name, if you look at this back page, here's a little summary of all the tests we just did. For y-axis symmetry, what you're going to do is look at your table or look at your graph, and if you see xy, then -xy will be on the graph. To do it algebraically, what you do is replace x for -x. Now for y-axis symmetry, it has another name. It's an even function. Even function. For origin symmetry, what you do is replace x and y for -x, -y. Origin is an odd function. For x-axis symmetry, you replace y for -y, or you look at your ordered pairs and see if the y values are opposite. For x-axis symmetry, it doesn't have another name. Does anyone know why they think x-axis symmetry? If we call y-axis symmetry even, origin is odd, how come we don't have a name for x-axis symmetry? Anyone think they know? It's not a function. Very good. Remember, this was one that was on its side like that, so we can't call it, it doesn't pass the vertical line test. This is not a function. So only these two have another name, even and odd. Even and odd. You gotta know, you gotta memorize the difference. So this is just a summary. So for your homework today, all you have to do is do the odds. If you need extra practice, do the evens. These came from your book. Read the directions. They're asking you in 1 through 4, does it have symmetry to the x-axis, the y-axis, or the origin? You have to do all 3 tests, okay? Now, for the one that says, neither, go to question 25. Some people were asking these questions. It says, determine whether the given function is even, odd, or neither. Neither means not the x-axis. A lot of people think neither. It means it's not even or odd. So for these questions, for even, what you do is see if it has symmetry to the y-axis. And that's when you replace x for negative x. Odd, you do both. You do x and y. You replace them both. If you get a no for both of those, then it's a neither. That's what neither means. Neither does not mean x-axis symmetry. A lot of people think that means x-axis. So your homework is attached. They come from the book. So if you have your book handy, on the odds, you can check your answers in the back of the book. Okay?